All right, moving on to the backside for number 11. We have a pot of boiling water. And when it was boiling, the temperature was 100 degrees Celsius, and it's now sitting in a room temperature room of 20 degrees Celsius. And the temperature of that water as it sits out, it's obviously going to cool. So the temperature of the water after H hours is given by this formula right here. And we're going to use that formula to answer parts A and B. Okay, so for part A, it says evaluate T of 2.5. So when you see something like that, I want you thinking about the play on words. So the 2.5 is obviously inside the parentheses, so it's the input. And in this formula, H is the input. So we're going to input that number for variable H. Now, when you do that, the formula is just going to read 20 plus the 80 times E, it says to the negative H. So for us, it'll be to the negative 2.5. Now, that expression, after you plug in 2.5, there's no like inverse operations here. This is everything on this entire side is just a number. 20 is a number, 80 is a number, E is a number, negative 2.5 is a number. All of this is a number. You can just literally put all that into Desmos. You're not solving for H. You already know what H is. So it's just 20 plus 80 e to the negative 2.5. Just type it all in and you get the 26.567. So 26.567. And then what this stands for, that's the answer that we got. That's the output. So that's the temperature in degrees Celsius of the water. And remember, we left it on the counter for 2.5 hours. We plugged 2.5 in for H. So that represents the temperature of the water after 2.5 hours. Okay, and that is it on that one. Then moving on to part B, we have T of H equals 52. So this time, notice 52 is on the outside of the equal to bar. So 52 outside is wanting to be the output of the model. So I'm going to purposefully put 52 on the outside of the equation. And this time I do not know the time. I don't know what H is. That's kind of the whole point, is I'm solving for that H value. So this time we need inverse operations. I don't know what H is. I can't put all this in Desmos at once. I'm going to have to use inverse operations. So the first thing we can do is subtract 20 from both sides, which would give us 32. I'm going to come up here. So 52 minus 20 is 32. I still have my 80 e to the negative h. Again, keep going with inverse operations, divide off the 80. Why? Because you can. Type that in the calculator, that fraction, you'll get a decimal of 0.4. And then this is the stage where potentially you're feeling stuck. You're staring at this and you're like, well, now what do I do? Okay, you're feeling stuck for a reason. You've done all the normal algebra that you can, and all that's left is the base of e, the exponent of negative h, and the desired result, which is 0.4. You're stuck for a reason. You've done everything you can. You're now looking at an exponential function that you don't know what to solve. That just means it's time to take the inverse. Now, similar as the other page, you could do a LOG, right? A log base E, but we're going to be savvy and we know that the inverse of a base E exponential is going to be ln. See, I don't have to write base E. Natural log by definition is base E. So just natural log for base E. Desired result is 0.4 and the exponent is negative h. So if you type the natural log of 0.4 in Desmos, you'll get negative 0.916. But notice that's still equal to negative h, and that's because there's one last step. You can think of that negative h as like a negative 1h. There's one last step, and that is to divide by negative 1, and that's how the answer just comes out to be positive 0.916. And then that represents the hours. So after 0.916 hours, the temperature of the can will be, or the pot, whatever it is, After 0.916 hours, the temperature of the water is 52 degrees Fahrenheit. Okay, last but not least, number 12, the relationship between an airplane's weight, which is W, and the runway length that it needs for takeoff, is a logarithmic function. So it says for some airplanes, the minimum runway length L, which is in thousands of feet, is given by this formula right here. And variable W stands for the thousands of pounds that the airplane might weigh. So part A, estimate the maximum weight of a plane that can take off from a runway that's 5,000 feet long. Okay, so 5,000 feet long, that is the length of the runway. That's the output. So this is trying, oops, I don't want the highlighter anymore. Undo, there we go. So this is trying to tell us that the output is 5,000. Now, remember, this model is already in thousands, right? L is in thousands. So I don't have to put three zeros, 5000. I can just put five. The model's already in thousands. So 5,000 on the outside equals 3 log W. Okay. Now, the most common mistake on this one, the most common question maybe is, well, there's no base. Students are like, Bishop, there's no base to this log. I can't even solve this. There's no base. All right, well, this is tricky, I admit, but we talked about it previous class. A common log is by definition base 10. Remember, if ever you just type log on a calculator, it's going to assume you're base 10. Regular log is assumed to be base 10. So since I didn't specify otherwise, you get to assume this is a common log, meaning base 10. So this is base 10. The exponent might be 5, the result might be W, but then what about the 3? He's neither a base nor a power nor a result. So that's why, similar to before, the first thing we're going to do is get rid of that 3. So I'm going to divide it off, inverse operation of multiplication. So now I've got 5/3 equals log of W. And now this is where you're officially feeling that stuckness again, if you will. You've got base 10, exponent 5/3, result W. You're like, what do I do? Well, you need to write it in exponential form. Base 10, exponent 5/3, result W. And 10 to the 5/3, guys, that's just a number. 10 to the 5/3, literally 10 to the 5/3. Done. 46.42 if we round it. 46.416 is, I believe, what the answer key says. So we'll go 40, what did I say? 46.416 is the weight. So then in terms of context here, remember that the weight, I believe, was also in thousands of pounds. Yes. W, thousands of pounds. So it's 46.16 thousand pound airplane needs 5,000 feet of runway. That was what the 5 stood for. The output of 5 was 5,000 feet of runway. Okay, part B, general inverse again. So the first thing we're going to do is just rewrite it. I'm going to drop the function notation. So it'll just be capital L. I'm going to drop the notation of L of W. Just put L equals 3 log W. Inverse operations, divide both sides by 3. So L over 3 equals log of W. Remember, we're trying to get W by itself. We're going to rearrange, invert this model until W is by itself. If you're feeling stuck, that's for good reason. It's because you're in base power result form, and all that's left is to take the inverse of the log, which would be the exponential. Now, again, I know it's not written there, but you get to assume that the base is 10. So this is a base 10 exponential. The exponent is that L thirds, and the result is W. And that might look weird. I can I can appreciate that, but mission accomplished. W used to be the input. Now it's on the outside. L used to be on the outside. Now it's the input. It's exactly the point of an inverse. It's the exact same model, it's the exact same operations, but inverted until the variables have switched roles. All right, and then last but not least, we can graph this function in Desmos. So what was it? 3 log W? So if I go into Desmos and graph, Desmos is a computer, not a human, so I'm not going to say L of W. I'm just going to say Y equals 3. It's a regular log, so you can either just type log or you can go into functions, obviously scroll down, but this time you wouldn't be choosing the log base button. You would just be choosing the regular log button right there. Um, Oops, I didn't mean to do it twice, but yeah, whichever. And then the input variable was W, but on Desmos, just a basic X. Okay, so this is what that model ends up looking like. And if I stretch, there we go, fix my axes just a bit here. Oh yeah, look at that. That's better. Okay, so you can see that this is an increasing function. Um, if you imagine tracing along this graph, it would indeed be going up, but notice it's going up at a lesser and lesser rate. So it's steepest in the beginning of the curve, and then it gets progressively less steep as the input increases. So when I sketch this, first of all, I'm just going to do a rough sketch of what I saw. So if I have my graph paper, it increases, but kind of, it's called concave down. We'll talk more about that in the next unit. Um, but what that means is, remember, this was the weight of the plane, and this was the length of runway. And they were both in thousands, 1,000 pounds and 1,000 feet. So, in terms of what this is trying to tell us, it's trying to tell us that as the weight increases, so the heavier the airplane is, the more length of runway you'll need. Certainly, heavier planes need longer runways. That makes sense. But again, you can tell that it's increasing, but by less and less and less. A normal exponential function increases more and more and more and more, right? Normal exponentials. But this isn't an exponential, it's a logarithm. So instead of increasing more and more and more, this one increases, but by less and less and less. So that's why we can say as the weight of the plane increases, as the weight of the plane increases, so does the length of runway required. But if we wanted to show off just a little bit, we could say, but it increases by less and less. So this like notion of increasing by less and less, it's a concavity conversation that we'll have more in the next unit, but I at least wanted us to like see that since these are inverses of exponentials, exponentials typically grow more and more and more and more due to the percent change. And so if you kind of think about it, it makes sense that the inverse of that is to still increase, but by less and less and less. All right, that's a wrap on the homework. Hopefully that was helpful. Thank you.